Okay. So the learning outcome for this chapter, thank you Lutfi, I think that was Lutfi. Solve problems on reflection and refraction, explain dispersion, tak payah, just explain this part. Problem solving tak payah, draw the ray diagrams, wajib tahu. Solve problems, wajib tahu. Draw the ray diagram for thin lenses, wajib. Solve problems on thin lenses, wajib. Okay, so historical development, we know that light, the scientists discovered that light has a dual behavior. It acts like a particle and also like a wave. So particle behavior dia lain, wave pun behavior dia lain. So with that said, light ni macam a lot of quantum effects are related to light, because it has that duality nature. So a lot of non-linear effects. So the part that we are dealing with in our syllabus is only the linear part. The non-linear part boleh simpan untuk degree lah. Kalau if you're interested, pursue physics or engineering, you will touch on this topic again, but in the non-linear punya effect. This part is only the linear, which means that it's not too complicated. Okay, so EM waves. EM is electromagnetic waves that are categorized by their wavelengths. Oh my God, I can't speak. So what we see around us is actually only visible light. So if I'm seeing a calculator that is gray, actually there's light that is being reflected into my eyes, and the light that is reflected into my eyes corresponds between 400 nanometer to 500 because it's gray, right? It's between purple to blue. So those are the wavelength that is reflected into my eye. If I'm seeing a cable that is white, so that's a different wavelength. If I'm seeing something that is blue, that is different wavelength. Everything that we see around us is actually the reflection of light into our eyes, and the reflection of light has a certain wavelength, and that wavelength corresponds to a certain color, right? You don't have to memorize this. I'm just telling you in general. Okay, so this is called the visible light. For UV light, you can't see it, but it's there. And then we also have infrared, X-ray, gamma ray, microwave, and so on. So these are the things that you can't see, the wave that you can't see, but the ones that you can see are called visible light. Okay. So in this topic, we will study on the reflection, refraction, and also dispersion a little bit. Wave optics for interference and diffraction, we will cover in chapter 12. So that is chapter 12. The first part is chapter 11. Okay, so here we have a spherical wave. A spherical wave propagates radially outward from the oscillating sphere. We've seen this diagram before from our sound chapter, where we had a source in the middle and our sound propagated outwards, right? Propagated outwards. And then we said there was a wavefront, and the wavefront is perpendicular to the rays, to the propagation. So a ray is a line corresponding to the direction of wave motion. So wave propagates outwards, so that is called ray. Wavefront is this guy. So what is this guy? Previously for sound wave, we said that this was lambda. For this topic, kita akan cakap, okay, so wavefront is a surface passing through points that have same phase and amplitude. So all the points on this part has the same phase and amplitude. Sebenarnya sama je macam lambda, tapi dia define in a different way. So has the same phase and amplitude. What is phase? If you do not remember that I told you from a lecture before, phase is when you have a reference wave and you have another wave that you want to compare your wave with the reference. Okay, ni reference. This is your wave. The second one is your wave. You want to compare it with the reference. If they start at the same time, they have the same phase. They have the same phase. If your wave starts at a later time, maksudnya dia start lambat lah, by 1 lambda or half lambda, doesn't matter. As long as you start earlier or start later than the reference wave, it means that you guys have different phases. So that is what it means by phase. If you start together, you have the same phase. If you don't start together, you have a different phase. So all these wave at this point, they have the same phase, and which means that they have the same amplitude. So kat sini amplitude dia sama. So that is what it means. So wavefront is when you have sama amplitude and sama phase. Okay? So far away from the source, the wavefronts are nearly parallel planes. So I'm here. So I have a torchlight. Let's just say I see the source. The source is next to me lah. The source of light is next to me, and this is the wavefront. The wavefront travels. The rays travel jauh gila semua sampailah saya tak nampak dah, and then it stops here. So my vision is limited because I'm a human. I can't see at the back. I can only see in the front. So from the front, I can only see that my plane is like, my wavefront is like this, which is almost like a straight line, almost lah. Kat sini memang nampak curve habis. This is still curvy, and then as it goes further away, it becomes less curvy. Sebenarnya dia curve je, tapi because my vision is limited, I can only see a small portion of that wavefront, and that small portion looks as if it's a straight line. Does that make sense? Okay, if I take this curve and I say, okay, I can only see this, I can only see this portion. Let's use blue. I can only see this, I can only see this portion. If I see this portion, I can almost say that, oh, it looks like it's a straight line. Tapi sebenarnya bila kita tengok the huge picture, it's a curve. But if I look at a small section of that wavefront, I look at it, oh, it looks like a straight line, even though it's not. Okay, so that straight line is perpendicular to my ray. My ray is the propagation of the light. So here it is 90 degrees. So rays and wavefront are perpendicular to each other. Are perpendicular. Okay, so they are perpendicular. All right. Okay, so that was the explanation. Ray of light is imaginary light. Okay, dah tahu dah ni. Okay, reflection and refraction of light. So light travels in a straight line path. So light ni nampak macam squiggle kan? This is wave. Tapi sebenarnya light travels in a straight line. It does not go zigzag like that. It travels in a straight line until it reaches a boundary, then something happens. Okay, what happens? Till it reaches a boundary, then something happens. So here, this is my incident ray. Okay, this is my incident ray. I shine it with a torchlight and then I draw my normal. Where should I draw my normal? My normal should always be 90 degrees to the surface of the, to the boundary. Sorry, 90 degrees to the boundary. So I draw my normal 90 degrees to the boundary. And then I can say, oh, this is my incident angle. My reflected angle will also be the same value. So if this guy is theta 1, this guy is also theta 1, my reflected angle. This is my reflected ray. Okay, so reflected in the same medium, of course, like I reflected always in the same medium. Reflected in the same medium, same angle as theta incident. Okay, so theta r is equal to theta incident. Okay, so here if this is theta 1, this guy is theta 1. If this guy is theta 2, my reflected angle will also be theta 2. So let's say I don't want it to be theta 1. I want it to be a different angle. So it's this much, and it is 60 degrees. My reflected angle will also be 60 degrees. Sama. Okay? Okay, let's say I have a surface and I have a bunch of incident rays. Where should I draw my normal? I should draw my normal perpendicular to the surface, but where? Let's use blue. Hello. Tak nak bergerak pula. Okay, so here is my incident. That is my normal. Here's my incident. That is my normal. So 90 degrees, 90 degrees, 90 degrees. Use your ruler. I don't have a ruler here. So angle theta 1, angle theta 1. If they are from the same source, then yes, they will have the same angle. If you are shining multiple torchlight on that boundary, you will have a different angle. But here, my point is you should always draw your normal perpendicular to the boundary. Where should you draw it? Of course, dekat your incident angle, incident light lah. Okay, if your incident light is here, draw it here, and so on. Okay, so that is reflection. What about refraction? So here kita tengok kat sini air, kat sini glass. So glass lagi tumpat dari air, alamak. Glass lagi tumpat dari air, which means that the speed of light will decrease. So mula-mula V1. So V2, the speed of light in glass will be slower than V1 because glass is more dense than air. When my V is smaller, my theta also becomes smaller towards the normal. When we are talking about light, we will always reference our angle with respect to the normal, not with respect to the surface, but with respect to the normal. So here, kalau tengok kat sini, my incident was like this. If this is glass, it will bend towards the normal. We call that bending towards the normal. Bending towards the normal, bending towards the normal. If my N is not glass, a different medium is used. Let's say this is glass and this is air. Maksudnya, the speed of light will increase. My theta will also increase. It will bend away from the normal. Bend away. So angle jadi lagi besar dari theta 1. Bend away. Angle lagi besar dari theta 1. Patutnya samalah. Sorry, tersilap pula. Okay, so padam balik. Bending away from the normal. Bending away. So it must. Susah yang lukis. Sekejap. Bending. Okay lah, bending lah tu. Bending away So maksudnya angle dia lagi besar daripada incident angle. That is bending away. So bend away from normal. When our speed is smaller, our angle is smaller. This is bend towards the normal. Okay, so this happens when n is greater. This happens when n is smaller. So dia terbalik dengan V and theta. Okay, so we had reflection. Reflection angle will always be the same because they are in the same medium. Property dia tak berubah. But when it travels into a different medium, the speed changes. The speed changes, which means that your angle also changes. If your speed decreases, your angle becomes smaller. If your speed increases, your angle becomes bigger. It bends away from the normal. Okay. So here is an example of a reflection, refraction, and total internal reflection. So I'm introducing a new term. If you forgot, I think you've learned this in high school, but never mind. So number 1 is incident ray. This is what I'm supplying this situation with. So this is my laser. Okay, laser pointer. Laser pointer? Yeah, laser pointer. Red laser pointer, I shoot it into a glass block. So I will have reflection, I will also have refraction. So where should I draw my normal? Of course, 90 degrees to the boundary. That is my normal. Can I extend it? Yes, I should extend it so that I know where to draw my refracted light later. Okay, so if my angle here is theta 1, my reflected light is also theta 1. Now, we can see that our incident angle is this much, and when it enters the glass block, the angle becomes smaller. So angle becomes smaller, theta 2 is going down. Maksudnya V should also be smaller. V is smaller. When V is smaller, N should be bigger. So N2, this is N1. So N2 should be greater than N1. Okay, N2 should be greater than N1. Because why? Because theta 2 goes down. Kita tengok sini, dia punya angle berkurang. Maksudnya speed dia pun berkurang. When our angle and speed decreases, our n should be greater than the medium that the incident light came from. Okay, so n2 kena lagi besar dari n1. Okay, so this is the conclusion that I get just by looking at this diagram. I know, oh, n2 should be greater than n1 because the angle is smaller. And when the angle is smaller, my speed is less. Okay, so that is refraction and reflection. So what happens over here? So I'm gonna, should I erase this or put this somewhere else? Sekejap, Oops, buang. Useless over there. Hello. Oh, dia tak nak. Dia tak nak berpecah. Hello, berpecah lah. Okay, dia tak nak. Never mind. Just gonna erase that then. Okay. So now let's take a look. Tadi we talked about the boundary between this dark area and the glass block. We don't know what the dark area is. It could be gas, it could be, I don't know, anything, right? So we figured out that N1 is smaller than N2, or N2 is greater than N1 because the angle was smaller. Now there's another boundary. There's another boundary, and this is now my incident light. So where should I draw my normal? It should be here. I can extend it sampai bawah. So this is my incident angle theta. Let's say it's theta 3. This is theta 3. Okay, so I have a reflection over here. Why do I not have a refraction? Where is my refraction? Okay, so this scenario where your light is totally reflected. Okay, so this is total reflection. Is called total internal reflection. Okay, kalau tak tahu juga tak tahulah. Nama dia dah bagi tahu siap-siap dah. Total internal reflection. Oh my god, I can't spell. So it's called total internal reflection, or TIR. Okay, we will talk more on this part later. But basically what you need to know is your incident light is all reflected within the same medium. The light does not break into reflection and refraction. Everything becomes reflection. So 100% goes to reflection. That is called total internal reflection. There's a certain angle before it becomes totally reflected. If it does not meet a certain angle, it will reflect and refract. If it meets this angle and goes beyond that angle, it will totally internal, sorry, it will do the TIR thing. Okay, we will talk more on that. So that is term, just throwing it out there for you. Siap-siap. Okay, so law of reflection. The normal is a line perpendicular to the surface. We talked about this. So it's always 90 degrees. It is at the point where the incident ray strikes the surface. So this is my incident. This is theta 1. Then reflected, sama. Theta 1 is equal to theta 1 prime. The reflected ray makes an angle, okay, blah, blah. The incident angle is equal to reflected light. We know this. Okay, so angle yang reflected sama dengan incident because they are in the same medium. The properties of light do not change. Okay, so refraction of light pula. As light travels from one medium to another, the wavefronts do not pile up nor are created nor destroyed at the boundary. Okay, light is a type of energy, which means that it can't be created or destroyed. If it is not being transmitted, it will go somewhere else. Okay, it will not disappear out of suddenly. It will go somewhere. If you can't see it there, it's somewhere else because it's an energy. So light is energy, which means that it can't be created or destroyed. So its frequency must stay the same. Okay, we've learned this about sound wave as well. When sound is transmitted, the frequency stays the same walaupun benda lain semua berubah. Sama juga wave light. Traveling through two different mediums, the frequency always stays the same. F always stays the same. Okay, and we know that the speed changes. Okay, if speed changes, our lambda also changes because V equals to F lambda. Okay, if F is your constant, V changes, lambda pun kena change. Okay, so frequency does not change, V and lambda changes if you are traveling through another medium. Okay. Oh, there's another equation I forgot. So this is an equation, your first new equation for this chapter. N1 equals to C over V1. What is it? N is the index of refraction. Index of refraction. Index of refraction. Okay, that is N. Okay. So what is N? N is actually a ratio of speed. So ratio of speed. Here you see C over V. C is the speed of light in vacuum. Speed of light in vacuum. I'm sorry, my handwriting is terrible these days. So this is the speed of light in vacuum. This is the speed of light in the medium. So, and the index of refraction is a ratio of speeds. What speed? The speed of light in vacuum versus the speed of light in the medium. And direferencekan to vacuum to get your, to characterize the index of refraction for that material. So that is how you get to know whether your material is lagi tumpat ke, lagi tak tumpat ke. So that is how they calculate for N. Okay, so that's your equation that you need to remember. Okay, refraction of light. Ooh, gambar ni kenapa macam funky? Oh, it is moving. I thought it was just my imagination. When light passes from one medium to another, it is refracted because the speed of light is different. So first, I started with my incident. Benda ni bukan goyang. It makes me dizzy. Okay, so it first started with theta 1. And then it, as I told you before, if my speed decreases, my theta also decreases. Okay, when light travels in a different medium, frequency stays the same, but everything else changes. So here, the speed changes, theta changes. The angle of refraction is less than the angle of incident. The ray bends towards the normal. Okay, I already talked about this with you. So here we can say that medium 2 has a greater N than medium 1. Okay, because it is bending towards the normal. V goes down, theta goes down, which means that N should be greater. Okay. Okay, next one. When light passes from one medium to another, it is refracted. Okay, ulang-ulang dah ni. Okay, but here dia cakap balik pasal equation N equals to speed of light in vacuum versus the speed of light in medium. Okay, so for a vacuum or air, you should remember this, N equals to 1. They won't give you, but if they do, baguslah. Tapi you are expected to know this on your own. So N equals to 1 refers to the index of refraction for air. The index of refraction for air, yep. Other media, such as glass or water, will have an N greater than 1. N is a unitless ratio, so it doesn't have any units. Okay. So here, this is a table that shows you the index of refraction for various materials. You don't have to memorize this, just general knowledge here. So diamond has 2.41, and you can see for, this is a solid. For liquid, such as water, is 1.33, so it's less dense. Then you have air as 1. Air and carbon dioxide are almost the same, except for the last, how do I say this? The fourth decimal place onwards is different. Okay. So solid is commonly known to have a higher refractive index. Liquid is known to have a lower refractive index than solid, but higher than air. And air, vacuum, reference point 1. Okay. Okay, Snell's law of refraction. I'm pretty sure you have learned this, but it's okay. We will learn it again. So normal incident ray and refracted ray lie on the same plane. Okay, this is normal, incident, refracted ray. All lie on the same plane. Maksudnya, Semua boleh lukis lah on the same plane. Semua boleh lukis atas kertas. Satu dimension. The incident ray makes an angle of theta 1 with the normal. The refracted ray makes an angle theta 2 with the normal. Okay, so that's straightforward. Padam. Jap. Padam. I don't like this. Let me choose pink. Okay. The ratio of the sine of incident angle to the sine of refracted angle is always constant. So this is Snell's law. So ratio of sine, okay, ni ratio of sine theta 1 over sine theta 2 is constant. That is Snell's law. So using Snell's law, you will solve for a bunch of problems. Okay, nanti kita akan tengok. So the bending of light is due to the change in speed. Berapa kali nak ulang ni? So the ratio sine theta 1 over sine theta 2 is equal to V1 over V2, but it is inversely to the index of refraction. Why? Because Snell's law says that N1 sine theta 1 equals to N2 sine theta 2. If I rearrange this, I will get N2 over N1 sine theta 1 over sine theta 2, which is why sine theta 1 dengan N ni dia terbalik. However, V1 dia akan sama, theta 2 sama dengan V. So maksudnya kat sini, sine theta 1, sine theta 2, kita ada N2, N1, V1, V2, apa lagi? Lambda. Lambda pun boleh jadi ratio. Lambda 1 over lambda 2. So here, the thing to note here is your 1 is, macam mana nak cakap, V dengan lambda sama 1, 1, 2, 2, but this guy is different. N1, N2 je yang lain. Okay. So that's another equation for you to remember. So sine theta 1 over sine theta 2 is equal to N2 over N1 or V1 over V2 or lambda 1 over lambda 2. Please do not say if theta 1 over theta sine theta 2 equals to N2 over N1 and then you say, oh doctor, sine theta 1 sama dengan N2 kan? Wrong. You can't say it like that. It doesn't work like that. It is a ratio. Kalau ratio ni tak ada, if you can't find the ratio, you can't solve. You just can't say sine theta 1 sama dengan N2. Salah. You can't say sine theta 2 N1. Salah. The only way for this to work is as a ratio. Okay, I cannot stress that enough. So let's say you only have sine theta 1, you don't have sine theta 2. And you only have N1, but you don't have N2. Then you don't have a ratio. You can't solve if you don't have a ratio. So kena ada ratio dulu, baru boleh pakai equation ni. Okay, if you have N1, you have N2, yes, it's a ratio. So you can find what is sine theta 1, sine theta 2. If you have sine theta 1 over sine theta 2, but you don't know what N2 is, yes, you can find out what is N2 because you have this ratio. Ratio tu kena ada. Kalau tak ada ratio, tak boleh. Kita akan buat soalan. So the frequency stays the same as the wave travels from one medium to another. Okay, I think at this point, I have said this for like 4 times already. But V equals to F lambda. So V berubah, lambda also berubah. Okay, so this is your equation tadi that we got from sine theta 1 over sine theta 2. Of course, there's a way to derive this, but I don't think it's important for, at least for this syllabus. So nak derive nanti, tunggu masuk kelas advance. So sine theta 1, sine theta 2 will give you these 3 guys. These 3 guys, 1, 1, 2, 2, sini, 2, 1, terbalik. This guy is the odd one, but it's a good odd. It's okay to be weird, okay? It works out. Okay, so example 11.1. A ray of light strikes a thick sheet of glass n equals to 1.5. Okay, so that's your first information. At an angle of 25 degrees with the normal. So let's draw it out. We have a glass. This is glass. And this is n equals to 1.5. Dia cakap incident. Dia cakap a ray of light strikes at an angle of 25, which means that the incident angle is 25, not the one inside the glass, but the incident. Okay, draw your normal, then draw your angle. Kalau tak draw normal lagi, jangan mengada-ngada, tulis angle. Okay, find the angle of the refracted ray within the glass with respect to the normal. So, assuming this is air, kalau tak cakap tu air lah tu. So this is air, so n equals to 1. N that is greater will make your V go down, will make your theta become smaller. So I have an angle, I have the light refracted towards the normal. It is bending towards the normal. So the theta 2 will be less than 25. Okay, it will be less than 25 sebab dia makin kecil. So how do I find out what is that? What is theta 2? I can use the Snell's law. Sine theta 1 over sine theta 2 equals to n2 over n1. Can I solve this? Do I have a ratio? Yes, I do have a ratio. This is n1, this is n2. So I have a ratio. So n2 is a 1.5, n1 is air, and theta 1 is 25. So this guy is 25. So solving for theta 2 should give me 16.4. Okay, so let's do that math. So sine 25 divided by 1.5. Inverse sine of that gives me 16.36. So this is 16.36 degrees, 2 decimal places. What should I say here? Apa yang saya patut tekankan kat sini? I forgot. N1 over N2. Okay, N is a unitless quantity. Did I miss anything here? Okay, good. All right, so let's move on. So to the next question. Water has an index of refraction of N equals to 1.333. What is the speed of light through it? So it's asking what is V in N2. So this is, so dia bagi C, dia bagi V1. So V1 is C. And we know that the speed of light is, C is this guy. Okay, this is the speed of light. Maksudnya dia punya N1 is equal to 1, right? We know that N2 is 1.333. We want to know what is V2. So using the ratio N2 over N1, remember dia kita balik, so V1 over V2. Okay, so please make sure that you know what is your 1, what is your 2, jangan terbalik pula. Okay, so plugging in those values, N2 should be 1.333 over 1 equals to V1. V1 is the speed of light, 3 times 10 to the 8 meter per second. And then I can find out what is my speed of light in water. So V2 should be, oops, sorry, 0.333, 3 times 10 to the 8 divided by 1.333. So you get 2.25 times 10 to the 8 meter per second. Okay. So pakai ratio je untuk these two examples. The first one was to use sine theta 1 over sine theta 2 equals to N2 over N1. And the second one, N2 over N1 equals to V1 over V2. Easy peasy. Okay, next example, a monochromatic light source. Okay, so what is a monochromatic light source? Mono means one wavelength. It means it emits a single wavelength or it emits a single color. So that is what a monochromatic light source means. It can be any color, but it will have a single wavelength. So a monochromatic light emits a wavelength of 490 nanometer in air. So this is n equals to 1, lambda equals to 490 nanometer. When passing through a liquid, the wavelength reduces to, let's say this is 1, this is 1, this is 429 nanometer. Okay, So dia tanya, what is the liquid's index of refraction? What is N2? So easy, pakai ratio je. N1 over N2, lambda 2, lambda 1. Mesti terbalik dengan N. Everything else sama kecuali N. N je yang terbalik dengan semua orang. So just plug in those values. So let's do that. Touch ke tempat. Let's use purple. So N1 is 1. I don't know what N2 is. Equals to lambda 2 is 4 to 9 nanometer over lambda 1 for 90 nanometer. Question. Should I convert this to a scientific notation or I can use it as nanometer? Do I have to convert it somehow or can I use it as it is? Can anyone answer me?
Let's use it.
Because?
Index have no unit.
Because it has no unit. Because it cancels out and leaves us with no unit. Betul. If, let's say, the question says 490 nanometer and 4.29 micrometer, can I use it as it is?
No.
No kan, tak boleh sebab it doesn't cancel out. What I'm cancelling out actually in here in this situation is 10 times minus 9, 19. 10 to the minus 9 over times 10 to the minus 9. So I cancel out because they are the same value. If they are not the same value, for example, this guy nanometer is 10 times 10 to the 9 and micro is 10 times 10 to the 6. So it's a different value, so I can't cancel that out. When that happens, you have to convert it to regular number, jadi scientific notation and calculate macam biasa. If both are in nanometer, yes, you can cancel them out. If both are in micrometer, yes, you can cancel them out because they are the same value. Okay? That's just FYI over there. So if you got this part right, the ratio right, you will get N2 as 1.14. Let me check. 4 to 9 divided by 490. 1 divided by that. Yep, 1.14. So betul. Okay, make sure your ratio is correct. Kalau ratio pun salah, salahlah jawapan. Okay, next one. A monochromatic beam. Mono. It's still a mono. Maksudnya it's a single wavelength. In air. So N equals to 1. So N equals to 1. Has a wavelength of 589 nanometer. In air. It passes through glass. N2 1.52. And then through carbon disulfide of N3 1.63. What is its wavelength in carbon disulfide? Okay, so how do we do this question? Can anyone tell me? Do we have the ratio?
Yes.
We do have the ratio. How do we use the ratio? Anyone? No one? Okay, there's two ways to solve this. First, you can solve N1 to find out what is lambda 2. N1 over N2, lambda 1, terbalik. Dia kena terbalik. Lambda 2 over lambda 1. And then, dah find out what is lambda 2. N2 over N3, lambda 3 over lambda 2. So first solve for lambda 2. And then dah tahu lambda 2 apa? Tak kat sini. Kita tahu up N2, kita tahu N3. So kita tahu boleh cari for lambda 3. However, there's another way to solve this, which is N1, N3, lambda 3 over lambda 1. It will give you the same answer sebab semua ni ratio. So ratio ni constant kan? So it will give you the answer. However, I am not sure if you use this method, boleh kena potong markah ke tak sebab tak tunjuk jalan kira for this part over here. So I will confirm back on this one. But to solve it, let's use the long way. Okay? Saya akan confirmkan balik if you can skip this process and just go to this part. But you can because it's a ratio. In math, it doesn't matter. Okay, the answer will be the same. So let's do this. So n1, n1 over n2, lambda 2 over lambda 1. So n1 is 1, n2 is 1.52, lambda 2 is, tak tahu, lambda 1 is 589 nanometer. Oops, nanometer. Can someone calculate what is lambda 2 for me, please? Okay. N2 over N3, lambda 3 over lambda 2. Anyone? N3.
387.5.
0.5 nanometer. Kan? Betul tak? Nanometer kan? Okay. 387.5 nanometer is your answer for lambda 2. And then N3 is 1.63 equals to lambda 3. We don't know. And we know lambda 2 is 387.5 nanometer. Because this guy is in nanometer, your lambda 3 will also be in nanometer. Can someone calculate lambda 3 for me, please? Sebab kita tak cancel out nanometer ni, kita tak convert dia jadi scientific notation. So what you get will be in nanometer as well. Dapat tak 361 tu? 361.3.
Dapat.
Alright.
Dapat.
0.3 nanometer. Okay, so let's say you terlebih rajin, you don't want to use nanometer, you can write it times 10 to the minus 9. So whatever answer you get, tak payah tulis nano pun tak apa, as long as it is in meters. So jawapan dia betul juga, even though you didn't jawab in nanometers. Okay, so that was that example. So now we are going into total internal reflection. When light moves from a medium with high index of refraction to one of lower index refraction. Okay, explanation ni panjang sangat. Saya nak cerita dia terus. Let's draw it. Okay, so total internal reflection. There's one condition that you must remember. Total internal reflection must come from an end that is higher. Must come, okay, incident light. Okay, incident light must come from n that is higher. Okay, so let's say that is higher. Sekejap, bagi saya habis tulis. Inilah dia kalau tangan lagi slow daripada mulut. Incident light must come from n that is higher. What that means is that if I have air and glass, if my light comes from air, I will not have total internal reflection. What I have is, I will get reflection and refraction. I will get that. If I come from air, if my incident light is from air, if my incident light is from glass, where the n is higher than air, right? I can get the total internal reflection. So this is my normal. This is my incident light. So mula-mula tu I will get refraction and reflection, right? I will get both. Up to one point, I will start getting total internal reflection. Okay, so ada satu point ni that when I meet a certain condition, all my light is reflected. Tak ada refraction, everything is reflected. Okay, so this can only happen if my incident light comes from an end that is higher. Okay, tadi saya start pada air, nak masuk glass, tak boleh jadi TIR. If I am starting from glass, going into air, yes, I can get TIR. So that is the first condition lah for TIR to happen. Okay, so let's take a look on how TIR works or how it starts. So let's, kat mana nak tulis that I have a lot of space. Kat sini je lah. Okay, so that is your first condition. Please remember. n1 must be greater than n2. Okay, so this is my n1, this is my n2. So now my n1 should be greater than n2. Okay, this is my normal. So first I start with an angle that is small. My incident angle is small. And then I start with, sorry, and then the second situation is my, lain pula angle dia. Kita buat semua satu tempat. Sekejap. Let me draw this properly. Okay, yes. First, I start with a small angle theta1, and then I increase my angle, and then I increase it even more. Okay, so let's see what happens. When I have a small angle, I will get my reflection. Reflection kena sama angle, forgot. Okay, so this is also theta1. I will also get my refraction. N1 is greater than N2. Maksudnya, this V is greater here. Theta is also greater here. Maksudnya, with respect to the normal, my theta2 will be greater than theta1. And then, the second situation, I increase my incident angle. What happens? My refracted angle becomes even bigger. Bila kita punya incident bigger, my refracted angle will also be bigger. Remember, it's a ratio. And then I also have my reflected light, which is the same value. Okay, and then the third situation, I increase my incident angle even more. What happens? Now my light is all over here. It just happens like that. When I reach a certain angle, all my light, tak ada reflected dah, but they are on the boundary. What is this called? This angle is called the critical angle. This is before you start getting total internal reflection. This is before you start getting TIR. This is called the critical angle. An angle that is greater than, an angle that is greater than critical angle will give you TIR. Okay, so now that we have found what is our critical angle, let's say it's 30 lah, contoh. Contohnya 30, critical angle kita. So now, kenapa selalu ingat ni tak faham. Okay, so now I have my fourth situation. I further increase my angle to become 45. Melampaunya 45 macam tu. Maybe that's 50 lah. That is 50 degrees. Is 50 degrees greater than the critical angle? Yes, it's greater than the critical angle, which means that I will get my total internal reflection. So everything is reflected. So this is TIR. No refraction at all. Okay, total internal reflection, total reflection of light back into the medium. Okay, so that is TIR. And when does the critical angle happen? This happens when, remember we have the sine theta 1 equals to, we had the ratio, where do I write this? Okay, we had the ratio N1 sine theta 1 equals to N2 sine theta 2, right? N1 is our incident punya index of refraction. Theta 1 is our angle of incident. And then our refracted light became 90 degrees to the normal. So N2 sine 90, N1 sine theta 1. When your light is sine 90, when the angle of your refracted light is 90 degrees, your theta 1 becomes critical angle. So N1 sine theta C equals to N2. Where is the sine 90? It's gone because sine 90 equals to 1. So sama je, times 1. Okay, so sine theta C equals to N2 over N1. So that is your critical angle for your TIR. Okay, now back to this equation. I told you TIR, the condition is N1 must be greater than N2. Kan? N1 must be greater than N2. So when they give you two N's, you have to figure out which one is, of course lah, tengok value je lah kan. Tengok value mana lagi besar, that should be your N1, N2 is the smaller guy. Okay, N2 should be the smaller guy. If you decide to derive your equation on your own, then you should know what to do lah. Okay, so boleh flip around. You can say N1 sin theta 1 is your refraction. You can see that. So nanti your equation berubah lah. But again, always remember your N, we start with this equation if you don't want to get confused. So N1, N2 sin theta 2. Salah seorang mesti jadi 90 degrees. Yang jadi 90 degrees tu, N dia kena kurang. So kalau you choose this guy to be 90 degrees, this is the guy that has to be the smaller index of refraction. Okay, vice versa. Okay, so what is the equation? Kejap. This guy. So sin theta C is N2 over N1. Take note, N1 should be greater than N2. So that is your equation. Okay, let's look at this diagram. So we start with N1. This is my incident angle. Ni gambar yang cantik sikit. And then it refracted. As the angle is increased, it refracted even more. As the angle increased even more, it became 90 degrees. This is your critical angle. This is where you achieve your critical angle. Going above the critical angle will give you total internal reflection. Yay. Next one. What time is it? Okay, half an hour to go. Okay, at a particular angle of incident will result in angle of refraction of 90 degrees. Okay, so what is the application of total internal reflection? It is your broadband, it is your internet. This is how the light signal propagates in your cable, in your optical fiber cable yang diorang gali tanah tu, they place this guy. But it's bigger because dalam satu kabel tu ada beratus-ratus optical fiber. Optical fiber is as thin as the hair. So light propagates in that optical fiber. Light propagates in that optical fiber as thin as hair. That is your internet. Okay, my field deals with that, but instead of using it for internet, I use it to make lasers. So that is my specialty lah, making lasers using optical fiber. Okay. And then this is fiber optics. You hear about fiber optic whenever you talk about telephone system, the cable TV system, or the internet. I don't deal with that. I deal with lasers. Okay, so what I do is I generate amplified light to shoot people. I'm just kidding. I use optical fiber to do the laser marking, laser engraving. What else? For manufacturing, drilling, cleaning, ablation. So lasers ada banyak sangat application. For cosmetic surgery, eye surgery, LASIK, semua pakai laser. Okay, not necessarily from optic fiber, but they are from the same family lah orang cakap. Okay, so ada banyak cara untuk hasilkan laser. Using the optical fiber is one of them. So if you're interested, boleh sama belajar dengan saya nanti. Okay, so let's talk about dispersion. Dispersion is when your light, the index of refraction depends on the wavelength. Okay, so let's see the definition here. Index of refraction N in anything except a vacuum depends on the wavelength of light. So dia cakap N is dependent on wavelength, on lambda. This is because of dispersion. This scenario is called dispersion. It depends, N depends on the wavelength. Kan pelik tu. Material depend on wavelength, but it happens. It is real. It is real. So this causes dispersion. Snell's law indicates that the angle of refraction made when the light enters material depend on the wavelength of light. Okay, for example, if I have a glass block and I shine two types of light, right? I shine red light and I shine blue light. So this is red and this is blue. So red and blue have different wavelengths. I can't remember, but they have different wavelengths. So because they have different wavelengths, this material, okay, this special material responds differently to the light depending on the wavelength. When light propagates in this material, the N becomes 1.5, okay? But when blue light propagates inside this material, the N becomes 2. So when this happens, this is called dispersion. The speed of light is different depending on the wavelength. So when speed of light berbeza, they don't reach the endpoint at the same time. They don't reach the endpoint at the same time because they have a different speed. So light ni instead of dia combine balik, dia berpecah because dia punya speed berbeza-beza. So they can't travel together. They have to separate. If I'm riding on a car and you're riding on a bicycle, we can't combine together. We can't travel together because our speed are different. You are going to be left behind while I will go further. So I can't wait for you, right? Because you are on a bicycle, I'm on a car. So I will reach my destination faster than you on the bicycle. So that is what happens here. So when we have different wavelengths, when we have different speed, we will have different speed, and it makes us propagate in the material either faster or slower. And when that happens, the light has to break. The light can't travel together. They will reach the endpoint differently at a different time. So that is dispersion. Okay. So Snell's law indicates, tak payah tu. Okay, so this is an example of dispersion. So here there is white light. First, we started with white light. White light, as you know, is a combination of many wavelengths. Okay, ada semua warna. The visible light that we see that is white is actually made out of a lot of colors, a lot of wavelengths. So when it enters the prism has a different N for different colors. So when it has a different N for different colors, the different wavelengths will have a different speed. And when they have a different speed, they will bend differently. Betul tak? Tadi kita cakap V increase, theta increase, V turun, theta turun. So sama juga, when your speed is different, your angle of deviation will be different. So when it finally gets out of the prism, light tu tersebar, it disperses. Okay, so that is how dispersion happens. Okay, so that's the general info for you. Semangat pula saya cerita. Okay. Rainbow later, kalau kita ada masa kita akan cover. This is dispersion. It's very interesting, but kita nak kejar syllabus dulu Nanti kalau ada masa saya akan cerita balik pasal rainbow. Okay, so let's do this example on total internal reflection. Diamond has an index of refraction. We have 20 minutes left. Diamond has an index of refraction n equals to 2.419. What is the critical angle for internal reflection inside a diamond that is in air? So we have a diamond that is in air. So ada light dalam ni. Ada light dalam ni. This is the boundary. Let's say. Tak tahulah light tu shine ikut mana, tapi let's just imagine it. Sekejap. As usual, I have terrible drawing. Please bear with me. Okay, so let's say our incident is this way. This is theta I. And I want to know what is the critical angle. What is the angle that gets my refraction light, that gets my refracted light to be at the boundary, right? That is the definition of critical angle. So sine n1, sine theta 1, and 2 sine 90. Okay, the 90 degrees to the normal, so that is 90. Which one is N2? Which one is N1? N2 is outside, N1 is inside. Sine 90 is the smaller n. Sine 90 is the smaller n, always. Okay, so smaller n. So if air is smaller than diamond, so N2 is air. So that is 1 times sine 90. Okay, so sine theta tak tahu, sine theta C, and one is 2.419. Okay, so now that you know which one is which, you can solve for theta C. Hello, kenapa tak boleh nak pakai pula ni? Theta C, right. So let's use our calculator. Sin 90 is just 1. 1 times 1 is 1 divided by 2.49, 2.419. Inverse sine, please make sure your calculator is in degrees mode. So that the answer is 24.4 degrees. Okay. Kalau ada soalan boleh tanya please just interrupt me. Okay, example, the next example. A ray of light travels across a liquid to glass interface. If the indices of the refraction, indices just means index, in plural form. If the indices of refraction for liquid and glass are 1.7 and 1.2, what is the critical angle at this interface? So here it's saying N1, which is liquid, is 1.75, N2 is 1.52. That's pretty rare. Misalnya liquid lagi, N dia lagi rendah daripada solid, daripada glass. But here the liquid is special lah. It has an N that is greater than the glass. So 1.75 for liquid and 1.52 for glass. What is the critical angle? And again, our smaller n gets the sine 90. So let's write that down. It gets the sine 90, which means that this guy gets 1.75 sine theta critical. Okay, so solving that should get 60.3. Let me check. Sine 90 times 1.52 divided by 1.75. Inverse sine of that will give me 60.29. Sama tak? Sama, 60.29. Okay, so theta C is 60.29. Okay. Again, emphasizing the smaller n will get the sine 90 in the equation. Okay, always. Next one, a fiber optic cable n equals to 1.5 is submerged in water with a smaller n equals to 1.33. This guy gets the sine 90. What is the critical angle? Sama je, senang. Kalau tak tahu lagi, tak tahulah. 1.33 sine 90. Again, sine theta C. And this guy gets the higher n. Okay. This guy is 62.5. Okay, any questions so far? I'm going pretty fast, I think. Ada soalan tak? Is everyone okay? Mengantuk?
Doctor,
Yep.
is there any question that we need to draw the incident line or the critical line? No.
Selalunya dia suruh solve
calculate.
pakai equation. Kalau drawing tu maybe sketch je kot. Tak payah ada protractor macam tu lah.
Alright.
Welcome. Any other questions? Everyone's tired. Sikit lagi. Lagi 15 minutes. Okay, next. Okay, so we are moving on to lens and mirrors. Kat asasi ada ke yang ni? Tak ada kot. Okay. So lens or mirrors. Light rays pass through lens. So apa perbezaan mirror dengan lens? A mirror reflects, which means that it does not let, if this is a mirror, light does not pass through. Sebab mirror is opaque, right? Ya Allah, kenapa je je? Mirror is opaque. Hello, where are you? Okay, this one. Mirror is opaque. If you have not noticed yet, you can't see behind the mirror. You can't see something that is behind the mirror, which means that light cannot be passed through. If you can see something behind the mirror, then it's not a mirror, it's a lens. Okay, so that is the difference between lens and mirror. Lens lets the light pass through. Mirror does not let the light pass through, which means that it's opaque. So, but it does not mean that the image cannot form behind the mirror. So we will see later on what that means. Okay, so we use ray diagrams to locate and determine the properties of the image formed by mirrors and lenses. And then we also need to accurately decide what is the position of the formed image. So it just wants to say, if you know the ray diagram, that's great, but you can't solve it if you don't know the equation. So you need to know both. Itu je lah maksud dia. Okay, so kena tahu ray diagram, kena tahu equation. So light travels in a straight line. We know this. It does not move in zigzag or something or in squiggly lines. It moves in a straight line in a homogeneous medium until it encounters a boundary. Sama juga. The ray approximation is used to represent beams of light. Bosannya nak baca. Next. Okay, a concave spherical mirror has a silvered surface on the mirror. Okay, basically concave means it caves in. Okay, macam cave, like cave kan maksud dia gua kan. Cave is gua. Okay, unless I got that wrong. But cave is gua, I think. So light, dia akan, macam cakap, converge. Dia, rupa dia macam gua kan, dia akan converge kan semua benda tu. Dia akan cuba compress. Dia akan converge lah, converge. So concave converges the light. Whereas convex, okay, dia diverge the light. So the way that I remember this is concave macam gua, dia kan converge light sebab gua suka tutup. Kononnya, I don't know if that is even betul. But that is how I remember it. So caves in, converges. The convex, the other guy, diverges the light. So diverge and converge. Okay. So this guy sebab dia suka terkeluar. Dia macam terkeluar macam tu kan. So light pun terkeluar, diverge. Next one. So that is the difference between concave and convex. So here parallel rays from a distant object are reflected by a concave mirror. So here rays of light travel in straight line until it hits the mirror. When it hits the mirror, it will converge into the focal point. Okay, remember light they travel in straight line sampai masa dia bertemu boundary. So the boundary is the mirror. The mirror is your boundary, and then what happens is that it will converge into the focal point. This guy is called the focal point. I believe you have seen this before. So this is called the focal point. Whereas for a convex mirror, the light diverges, right? So light travels in straight line until they meet a boundary. The boundary is the mirror, and then it will diverge. But which way is the diversion? The diversion will be with respect to the focal point. Okay, and the difference between the focal point of concave versus a convex is that the concave punya focal point is real. What is real? Real is when this is us, this is the mirror, the focal point is in the same place as us. Okay, so I am in front of the mirror. If the focal point is in the same dimension as I am, it's called real. If the focal point is behind the mirror, which is somewhere that I can't be, it's called virtual. So here, the focal point is somewhere I can't be because obviously I can't go behind the mirror or inside a mirror. So that place is virtual. So if I have a focal point in the virtual place, I can't say dimension, that will be too sci-fi. If I have a focal point that I can't reach, it's in a place where I can't reach it, I can't touch it, it's virtual. If the focal point is in front of me or in the same place in front of the mirror, it's called real. So a real focal point is positive, a virtual focal point is negative. Again, real if it's in the same place as I am. By place, I mean in front of the mirror. And if it's behind the mirror, then it is virtual. I can't be behind the mirror, so that is virtual. Okay, real, positive F, virtual, negative F. Concave, converge, convex, diverge. Okay, so focal length, the distance from the mirror to the focal point is called the focal length. Okay, we label it as F. Okay, 2F is called the radius of curvature. Oh, kat sini dia panggil center of curvature. So there's two names to it, radius of curvature, radius of curvature. You can label this as R, or the center of curvature C. Sama If they label as R or if they label as C, it just means the same thing, which means that it is twice the length of your focal length. Twice the length of your focal length. Okay. Selalunya focal length ni akan diberi selalunya, unless they ask you to find what is your focal length. Okay. So it depends on what type of mirror that you use. Each type of mirror, they will specify what is the focal length. Okay. So the focal length is half the radius of curvature ataupun 2F equals to R, which I wrote over here. Okay, I think this is much more easier to remember. So 2 times the focal length is C or R. Okay. Apa lagi? C, focal length, R. Okay. Okay, so this is an example of focal length of a spherical mirror where the focal point is real. Okay, so if I am here, the focal point is in the same dimension as I am. That is a real focal point. Whereas I am in front of the mirror, but the focal length is behind the mirror. That is when our focal point is at the virtual and it is a negative. This guy is a positive. Okay, semua orang faham virtual dengan real tu macam mana? Sekejap anak saya. Kejap. Okay, virtual and real. So that is what it means. So if my focal point is in the same area as I am, it's real. If it is not in the same area as where I can be, it's a virtual. Okay. Okay, now we are going to learn how to draw the rays for a mirror. But first we have to draw the structure first. So we start with pole. Pole is the center of the mirror. So if you have a mirror, this will be your pole, the center of the mirror. And then you will have a principal axis which goes through this pole. Okay, dia tak go through betul-betul pula. But it basically goes through the center of the mirror. That is your principal axis. Okay, so that's your principal axis. Pole and principal axis, PA. And then you have your focal point. This guy is if I am over here, which means that drawing this type of mirror is concave. If I want to draw a convex lens, it should look like this. Okay, diverge, right? This one is converge. Okay, just showing it to you. Let's go back to concave. So concave focal point is in the same area as I am because it's real. So that is F. If F is this much, 2 F's will give me C or R. Okay, so that is your C. Focal point, central curvature, C. Okay, so we have drawn the structure for a concave. What about convex? So convex, what is the center, principal axis? Center is pole, principal axis goes through the pole. And if the object is in front of the mirror in this place, which means that the focal point should be behind. Lama tak cukup tempat. Let's say the focal point is kecil je lah. So focal point is here, which means that 2 focal point is C, center of curvature or radius of curvature. The rays will diverge, okay? So let's see how to draw that. Next one. Ray 1 is drawn parallel to principal axis and reflected back through the focal point. Ray 2 is drawn through the center of curvature and reflected back onto itself. So how does that look like? Selalunya kita akan memorize ray 1 and ray 2. Ray 3 selalunya kita tak buat. Kita buat 2 rays je because we already get the answer by just drawing 2 rays. So first, this is your object. And this is a concave lens, concave mirror, concave mirror. So draw your light. If you want to draw the top part of your object, so you will get the top part of your image. If you start with the bottom part of your object, you will draw for your bottom part of your image. If you draw the center, you'll get the center. So people will usually draw the top part of the image because it lets them know what is the height of that image. Okay, so start with the top part. You can do whichever one that you want, but you have to know what it means. So start with a parallel line. Rays travel in straight line until it hits a boundary. So the boundary is the mirror. When it hits the boundary, it goes through the focal point. So that is your ray 1. Ray number 1, done. Ray number 2 goes through the center of curvature and back onto itself. So goes through C, hits the boundary, goes back onto itself. So now the place where ray 1 and ray 2 intersects is where your image is, buruknya. Is where your image is. So they intersect over here. So remember, I started with the top part of the object, which means that the intersection between the rays will give me the top part of the image. So top part of the image. So this means that my image is inverted, right? So if I want to draw the center part of my image, I just want to make sure if I'm doing this right? So we can do that. Let's do it. So if I am finding out the center point of my image, so this guy is my center point. So straight line until it hits a boundary, goes into the focal point. Goes into the focal point. Goes into the focal point. Okay, good. That is ray 1. And then ray 2 goes into the center of curvature back onto itself. Okay, so from the center of the object goes, this is so hard, back onto itself. So, tak intersect pun. Sekejap. Okay. So the intersection is over here, which is approximately half of the object. So I started here, right? I wanted to map out where is the image at the half. I wanted to map out the half of the image. Okay, so kita pergi dekat half of the object, draw, hit the boundary, go into focal point, go into C, back onto itself. So the intersection between ray 1 and ray 2 will give me the middle part of the object. Okay, so we figured out the top part of the object, we figured out the center. Okay lah, legit lah maksudnya our drawing is correct. So that is how you use it. But usually you just solve for the top part of the object and you are good to go. Selalunya nak cari center point tu nak tengok balik je, okay ke tak, betul ke tak. Just to confirm. Okay, so that was for concave. What about convex? We have 5 minutes to go. I'm going to stop right now. We will continue next class tomorrow. So any questions before we end class? Stop sharing. Is everyone okay? Was that clear? Was I too fast? Stop recording. How do I stop recording?